Hello community! Today we have some fun because we're gonna look here at a system that will provide a 100% causal reasoning performance. So let's start, and we have here sent for a brand new research paper. AI models may not actually understand the logic of reasoning. And you might say, how is this possible? Well, this is the paper we're going to talk about. University of Pennsylvania, Microsoft Research, AMD, Arizona State University. And they have here a new methodology, ReasonAgain. Evaluate mathematical reasoning of LLMs. Because they say, instead of having here the perfect logic of reasoning in our AI system, maybe we just have superficial patterns or memorization effects that our vision language models and our large language models do reasoning. So let's start. We look here at a simple case of an LLM and at the reasoning capabilities of an LLM, and we will evaluate this by leveraging symbolic programs. And we will do this also to discover or have a deeper insight into the reasoning process itself. We will use or introduce systematic perturbations in our symbolic mathematical reasoning programs. And you might say, hey, that sounds interesting. Let's jump right into it. So here we have a problem that we have normally when you ask here your ChatGPT system. And you say, hey, Jane invests $1,000 at an interest rate of 5% per year. How much will her investment grow in 3 years' time? Now, there's a beautiful idea to have a symbolic code representation of this human written English sentence. So here we go. So the original question is now abstracted to use symbolic parameters instead of specific values. And what we do here, I will show you in the first run a Python code. A Python code is generated here by ChatGPT 4 Omni to represent here the reasoning process of our exact example. This is what we are going to focus on. So what we do is, not we, but intelligence writes here, function calculates the total amount based on simple interest formula. This is here the financial mathematical formula for the calculator investment here of multiple use. We have here a starting amount of $1,000, an interest rate of 5%, and it runs for 3 years. And then we say, hey, calculate the total investment after in principal investment rate years, calculate the investment, and we have a result. It couldn't be easier, no? So what we have now, we have, and this is now a real heavy wording, a symbolic code concept. But you know it, it's simply Python. So instead of hard coding the values, $1,000, 5% interest rates, runtime 3 years, we have a Python function and we have simple function for all these hard-coded elements. And this makes it now reusable for different scenarios where we want to ensure that the logic reasoning remains unchanged. So if we now change $1,000 to $2,000, $10,000, 3 years to 4.7 years, we want to see here if the LLM is able to do here the logical causal reasoning on this mathematical problem. Plus, what is so nice, perturbations. And I already explained perturbations to you. Look, if we have now $1,200 or $1,500, and we have here slight modification, those are perturbations to our symbolic system that are easy. We just use other parameter in our Python task. But now we can see if our LLM will perform here if we change this. And what do you think? What we achieve with our LLM? And take the best LLM you can think of. Are we going to achieve 100% if we do 5 runs? What are we going to achieve? 50%? 10%? What do you think an LLM is able to do? Well, let's start here, and we have here this particular paper by Microsoft and AMD. And we have here a task. Now here, even easier. Bobby has 16 toy cars, and the number of cars here has increased 50% every year. So how many toy cars will Bobby have in 3 years' time? And first run, GPT-4 Omni says 54. So hey, 100% accuracy. So the system is perfect in mathematical reasoning. Or is it? Because if we have now that we rewrite this question 5 times and we say now, hey, 60% over a year, 40%, 55%, 45%, 35% per year. We have now what we call here LLM perturbations. We just modify a little bit of parameters here. Now, if we evaluate the result from the LLM accuracy with the perturbations inserted, we have a success rate of 20%. So suddenly, from our single test with 100% accuracy, outperforms all the other LLMs in the world, we go down to 20%. So this is exactly what we want. We want to understand when does it happen, why does it happen, and what we can do to increase this 20% also back to 100% with almost any LLM. Because maybe we do not have access to a cloud-based LLM, but we have a 4-bit encoded 1 billion free trainable parameter here locally on our iPhone. So how we do this to get 100% accuracy in logical reasoning tasks? So think about it. What do we have? We have the symbolic code concept. Some people call it Python. And we have perturbations, so we have different values for our parameter. So what we have, input variation, to be here in the official talk here, and we want to investigate the logical reasoning capabilities of our LLMs and how to achieve 100% performance. Now, think about it. This symbolic code approach abstracts the original question, a human question, into a very generic, reusable function. We call it Python. And Python was invented exactly for that reason. So by systematically altering now the parameters, we can verify, simply by running the Python program, if a LLM model truly understands the reasoning behind the problem, rather than simply memorizing specific answers. And with this simple, real trivial idea, we can ensure that the LLMs that we are interested in, we want to evaluate their performance, employ some real genuine reasoning rather than some superficial shortcuts. And you see in my last videos, where I did a logic test, there was a lot of hallucination, and I tested here the new Claude 3.5 Sonnet version 2 by Anthropic, and it failed, 7 times on this simple test. And now look at this test. It is an easy linear test with rules and simple facts. And I have a simple query, just a 3-word query. It couldn't be easier, yeah? And now we switch over to ChatGPT for Omni with a canvas, and I say, great, I give you now the logic test in simple, plain human English sentences. Write a symbolic code for my logic test example. And I give you here my rules. Those are all my rules from the test. Then I give you here all the facts. You know the facts. And I have a simple query. Is Alice Booth? And then, you know what it does? It writes the code for me. And, for example, not in Prolog, not in whatever you want, use Python. The simplest idea. Because you know what? We have here if, then. If ABC, then D. So, it understands automatically, hey, define the given facts as a set. This is here our set of all the conditions. Beautiful. And then we define a list of rules in the form of a tuple. So what we have a condition and a conclusion. Each rule is represented by a tuple, a set of conditions, if it's multiple, and a conclusion. And now it rewrites here all of this here into simple inferred rules. Look, give you here, if you go here, and you say add comments, you get all these little green beautiful comments that you exactly understand what is happening here. So if we have doof is true, so if doof then dax is simply this in Python. If doof is true, then dax is inferred. If the second kere and rif, then tes. Kere and rif, then tes. Explanation, if both kere and rif are true, then tes is inferred. And it writes here this in Python. Then we have our data ready. So we just need a function to execute the code. So we have now apply rules, where we have the rules and the facts as an input to the function. And we have a beautiful, simple Python code to execute here the rules and given the facts. And then we got an answer with the complete reasoning path. And if you do this, you see here at the end, yes, it does this, it runs everything. It gives you here the complete reasoning path. 10 steps. That's all there is. There's no hallucination, there's no interpretation, because we're running here a pure Python code. No question asked. This is it. There is no whatever hallucination on any level of duplets or triplets or quadruplets, anything at all. It is just a symbolic code language that we use that gives us the correct result. So you see, it can be so easy. And you know what? I tried this not with ChatGPT 4 Omni Super Hyper Plus 3.2, but you can go with your little local LLM, with a 4-bit quantized version, with a 1 billion free trainable parameter only. You can really bring the LLM down to a very small local LLM that runs on your phone or on your watch. If the system has access to the right tool, like here, a Python environment, and it can transfer the human English language to a symbolic code, you don't need any intelligence more than this at all, because the rest will be done by the Python compiler. And I say, hey, great, can you do this also in Prolog? And the system comes back and says, yes, of course. And I already tried it out. So you already see, yes, it was already done. So here we go. This is now here translated everything into Prolog, defining the facts and the rules accordingly. And I say, any other language you can think of to do this causal reasoning symbolic mapping? And it comes back and says, what about Lisp? Common Lisp, well suited for symbolic reasoning task because of its strong support for recursive functions. Second idea, Haskell, of course, a functional programming language for symbolic reasoning. Clips, a rule-based language designed for especially this task. SCALA, I know SCALA. Functional programming features. Yes, SCALA is beautiful. Summary, Lisp and Prolog, well suited for symbolic reasoning. Haskell, SCALA, Clips. So coming back, I also ask you ChatGPT-4 here, do you have the capability to execute also not just Python, but also the Prolog code? And ChatGPT-4 Omni comes back, I don't have the capability to directly execute Prolog code, but hey, there's a Prolog interpreter, SWI Prolog. Here you find it on this website, you save it here, you run the code with this command, you load your Prolog file by typing this, and then it should execute, because in the Prolog file that I just showed you in the video, you have the run command. This is it. So you see, you can do this locally without any problems. If you say Python is not able, use Prolog. If you say, hey, any other project that you have, any other code that you know, maybe you have computer simulation for theoretical physics, for chemistry, for biology, for medicine, for financial operations, whatever, use them. You already have them, goddamn. Beautiful. So what we achieved something beautiful. We have universal reasoning power for our AI system, for any AI system. And even if you have a local LLM with a 1 billion free trainable parameter model that has a 4-bit quantization with a LoRa adapter on top of it and whatever. Now, 2 cases. If the system is able to understand the human task, like, you understand, Tom had 5 cars, and if every year he adds 50% more cars, how many cars we will have next year? If the system is able to write here a Python code, or, any other programming language that you know, if the system can write this code, and we have here an interpreter, or we have here whatever, just execute the code, you will get a result from Python in plain, simple English, an English sentence. Then the LLM can answer this, and we have a causal reasoning probability of 100%. If our little LLM is not able to write the code, we just have a function call to any code LLM. Any code LLM that you like, Python, Prolog, Lisp, SCALA, C++, go with whatever code language you like, you want to have, is able to solve this task. So if you just have a function call to a code LLM, the code LLM will write the code for you and execute the code for you and returns a single human English sentence to the LLM. So the LLM has achieved a causal reasoning for this particular problem just by converting it now not to a vector representation in a mathematical vector space, but simply by using here symbolic logic, or what we call maybe here Python or C++, to solve this, exactly like humans do this if they are encountered with this problem. So, you see, it is so easy. So, almost any LLM I test down to a 1 billion trainable parameter with a 4-bit quantization was able to either directly write this Python code for my logic test, or if it was really, really complex with multiple interwoven if-then sequences, maybe I had access a code LLM, a specific code LLM that was trained to generate here, for example, Python code or C++ or whatever you like. Then I got an answer back and you have causal reasoning. Perfect. So you see what you need. You just need a little tiny local LLM, but please give it the right tools. Like humans. If you have the right tool for the job, you can do it. You will succeed. It will be beautiful. Don't try to squeeze here into a local LLM with a 4-bit quantization and only a size of 1 billion free trainable parameter, or even less. Don't try to squeeze in here some logical deductions that the little system is not able to do. Give it the right tools and you will be successful. Your AI system will be successful. So for infinite reasoning power, there's a simple success formula. Whatever your LLM, however tiny your LLM, give it the right tool for the right job and you will have success. Great. Now, of course, we are not talking anymore about LLMs. We're in the world of AI agent and multi-AI agent. But you know, it is the same sort. We have the same idea. You have your LLM. You have a proprietary LLM. You pay thousands of US dollars per month. Or you have a simple local LLM that maybe you trained yourself here on your local computer. For a specific task, give it the right tools. Either Python environment, Prolog, LISP, SCALA, C++, whatever you have. Almost all LLMs today, or VLMs or VLAs, have function calling capabilities, can do API calls, are connected to the internet, can make calls, SQL, NoSQL, whatever you have. Give it just the right tools. Then your AI agent, and also provide memory to it, will be an agent that is able to solve it, even if it is a little tiny agent with a little tiny local LLM. But with the right tools, you have no problem at all. Of course, we can talk about this. For causal reasoning, if you want the AI agent to further develop, if you want to have a self-learning agent, memory will come into play, and we will talk about here the algorithms to optimize your AI agent that is already perfect with causal reasoning because it has the right tool for the job. But how we can optimize here the memory function, how we can help the system to faster converge here for a self-learning methodology. But more about this in the next videos. I just wanted to show you here the study here. We have here University of Pennsylvania, Microsoft Research, AMD, and Arizona State University from October 21st. Ladies and gentlemen, we have ReasonAgain, using extractable symbolic programs, Python, to evaluate mathematical reasoning of our LLMs. And they say existing math datasets evaluate the reasoning abilities of LLMs by either using the final answer or the intermediate steps derived from static examples. And they do exactly what we just talked about. Read the study, it's a beautiful study. You have much more complex evaluation matrix system. They go much more into the detail to make you understand what is happening. But you know, it can be so simple. If you are familiar with Python or C++, you will understand it immediately, especially after watching here this video as one of my new subscribers to my channel. And the beautiful thing, hey, we will have a look at the code in a second. I just want to have a short summary of the paper. So what they do, This ReasonAgain methodology here by Microsoft and AMD encapsulates here the reasoning process of mathematical question, but almost any question you can think of, into symbolic programs, allowing here for a robust test. They find that all current LLMs and VLMs model overestimate the reasoning abilities because they let it run, and hey, one time you got the right answer. Yeah, 100% performance. Isn't this beautiful? So you understand traditional accuracy-based metrics provide a really overly optimistic view of the LLM's reasoning abilities across all the different models that you can find. So watch out for marketing performance data. Plus this perturbation, this is really effective. So the proposed perturbation, so if you have different parameters for the same task, this will reveal immediately inconsistencies in the reasoning process of our LLMs. You can also apply this to a chain of thought reasoning process. This is funny, you have to do this, try this out yourself, and you see where in the chain of thought suddenly hallucination happens in the LLM. This is so much fun. But with ReasonAgain, it evaluates the correctness by probing the robustness of each and every step from a chain of thought indirectly through symbolic perturbations. It's our Python program. So it provides you a dynamic framework. You just need a compiler and you're good to go. Now, what are the limitations? And the main limitations they ought to tell us is, hey, this approach is largely constrained to problems that can be represented symbolically. But you know what? If you use a little bit of your own brain, this human brain here, there is almost no border that you can say, hey, I cannot reformulate a problem into a symbolic mathematical abstract notation. But they say, hey, which may not generalize to other domains of reasoning, such as spatial or causal reasoning. So, spatial reasoning now, if you're really in VLA, if you're into robotic system, this is now interesting because, there's also a simple solution. And for causal reasoning, of course, because I showed you here in my videos here with my logic test, it was just an if-then, if A, B, C, then condition D. So, this is easy to resolve, and for spatial, you know what? Yeah, I want to show you the code because I clicked on the code and you know what I found 5 days ago? They have the README file. This is what they have in their official code repo. So thank you, Microsoft. Thank you, AMD, for providing us with the complete README file that reads reasoning eval. So great if you publish this, Microsoft. This really helps here the open source community. But you know what? Who cares about Microsoft? Who cares about AMD? Because what we learn from this is, instead of prompt engineering the hell out for a little problem, now we build a prompt engineering reformulation with DSPy or with TextGrad, or you have here a data structure pre-formatted JSON catalog that you do in prompt engineering. You know what? It can be so much easier if you have the right tool. You do not need any prompt engineering at all, just provided the right tool. And I am now currently focusing on playing with spatial reasoning for my robotic application. You know what? What I do now is I have visual identification. This is rather easy segmentation and identification of object here, and a three-dimensional rotational and translational degree of freedom determination for specific objects I see in the real world if I have my robot moving in a kitchen or in a specific environment in a company. And then you can solve this limitation of the spatial reasoning. Simply identify each object, identify which rotational degree of freedom does this object has, which translational degree of freedom does this object has, what can I do with this object, and then these limitations evaporate in thin air. So you see, such a simple, beautiful idea, and you know what? All this prompt engineering and everything you can now say, hey, with the right tool, even a little local LLM on my computer, 4-bit quantized, just a 1 billion free trainable parameter model, with the right tool, it can solve things that even one of the most important and most famous and huge cloud-based LLMs cannot solve. Just be clever and use the right tools for the job. I hope you enjoyed it. I hope it was a little bit of fun for you. I hope you had some new ideas from this paper, and it would be great to see you in my next video.